Propagation concepts. Learning objectives. By the end of this topic, you will be able to describe the concepts of propagation, explain applications of skywave propagation. Concepts of propagation. A transmitting antenna with transmitting equipment at one point and receiving antenna with receiving equipment at the other point are necessary to establish a wireless communication between 2 points at a distance. The transmitting antenna radiates a radio signal in the form of an electromagnetic wave. The wave consists of two types of fields, namely electric field and magnetic field. These two fields are mutually perpendicular to each other. Both these fields are time-varying fields, and the lines of force of these fields are perpendicular to each other. The direction in which the electromagnetic wave travels is perpendicular to both the fields simultaneously. In other words, the electric field and magnetic field and direction of wave propagation all are orthogonal to each other. That is, if x direction represent electric field, y direction represent magnetic field, and the wave propagates in z direction, then it is called as TEM wave. The electromagnetic wave travels in the free space with the velocity of light, that is, c is equal to 3 into 10 to the power 8 meters per second. As the wave travels through the free space, the strength of the signal reduces. Such signal gets intercepted by an antenna at the receiving end. As such, an antenna is a conductor basically. A voltage is induced in it, which is used in the receiver for process. If antenna is considered as a point source, then that point source radiates electromagnetic waves in all directions uniformly, thus giving a spherical wave front. Therefore, the signal received at the receiving end is very weak. Even though the wavefront from the point source is spherical, for a small area, a point located at a large distance from the source, the wavefront is a plane wavefront. Applications of skywave propagation. Radio waves in the low frequency, that is LF, and medium frequency, that is MF ranges may also propagate as ground waves, but suffer significant losses or are attenuated, particularly at higher frequencies. A new mode develops, that is skywave, when ground wave fades out. Sky waves are reflections from the ionosphere. When the wave is in the ionosphere, it is strongly bent or refracted, and it is ultimately sent back to the ground. From a long distance away, this appears as a reflection. In this mode, long ranges are possible up to hundreds of miles. When the concentration of ions is not too great, sky waves in this frequency band are usually possible at night only, since the ionosphere also tends to attenuate the signal. However, at night, there are just enough ions to reflect the wave but not to reduce its power too much. The high frequency, that is HF band, operates almost exclusively with sky waves. The higher frequencies have less attenuation and less refraction in the ionosphere as compared to medium frequency. At the high end, the waves completely penetrate the ionosphere and become space waves, where at low end they always reflect. The high frequency band operates with both these effects almost all of the time. The characteristics of the skywave propagation depend on the conditions in the ionosphere, which in turn depend on the activity of the sun. In high altitudes, ionosphere has several well-defined regions. Summary.
Let's summarize the topic.
The transmitting antenna radiates a radio signal in the form of an electromagnetic wave. The wave consists of two types of fields, namely electric field and magnetic field. The electromagnetic wave travels in the free space with the velocity of light, that is, c is equal to 3 into 10 to the power 8 meter per second. As the wave travels through the free space, the strength of the signal reduces. Radio waves in the low frequency, that is LF, and medium frequency, that is MF ranges may also propagate as ground waves but suffer significant losses.